Well, good morning, Mike.
Good morning.
Good morning, everyone. So now it's 6 o'clock UK time, and I'm going to hand over to Mike Wall, who's presenting speed and angle of blow assessment. See you later.
Thank you. Welcome to Thailand, hot and sunny Thailand right now. Just finished the rainy season, into the hot season now. Firstly, I'd like to thank the IIMS and Mike Schwartz in particular and his team for organising the event and for inviting me to speak, and also to commend the previous speakers and those to come for their courage in doing this. This is the one way of proving to people that you are worthy of the title marine consultant, by proving that you are capable of doing these things and you have the expertise. So no more ado, let's get on with it. Oh, here we go. The history of speed and angle of blow assessment. Right, with the advent of nuclear power plants, this brought about the design of the first nuclear-powered merchant vessel, which was the Savannah. She was launched in 1959 and designed with nuclear power plants supplying steam to turbines. That's the ship, and back in 59 she really was modernistic. She was more like an ocean-going trawler, really. But the problem was the possibility of a reactor being penetrated during a collision with another vessel, particularly with a naval vessel which might have a sharp bow. So the first research was carried out by Mr. Minorsky and later by Captain T.D. Halla. The research was carried out into the strength and scantlings requirements for nuclear vessels in order to safely absorb the kinetic energy of a collision, particularly with a warship which might have a sharper bow. Minorsky is seen as the authority on the subject, having derived a relatively simple methodology. So here we have the bow of a typical striking vessel. The bulb actually here is being moved back a couple of meters, moved up a little bit, and moved over to the port side slightly. This is the other vessel, the struck vessel. As you can see, this is, I think this is number 3 and 4 holes, which now have beautiful indoor swimming pools. The collision usually results of a failure to comply with collision regulations or a breach of duty to exercise good seamanship. Excuse me. In most cases, both vessels will be to blame, there never being one vessel 100% to blame. In most jurisdictions, each vessel will be liable in proportion to their degree of blame. The vessel claiming compensation for loss or damage will have the burden of proving the other vessel to be negligent. Consequently, events leading up to the collision must be established as far as possible. Witnesses interviewed, logbooks and records retained. However, the facts are often found to be in dispute between the parties involved, with contradictory statements. It may therefore be difficult to make accurate estimates of times, distances, bearings, speeds, and course alterations. The lawyer will be appointed on behalf of each vessel and other interested parties, for example, owners, underwriters, P&I clubs, cargo underwriters, and charterers, etc. He will usually take statements from crew members, particularly the senior officers and those witnessing the events. He will obtain other information, for example, the logbooks, the plans, and other records, which will be useful in our calculations. He will also need a quick assessment of cost of repairs to set security from other vessels' owners. The marine surveyor will be appointed by each of the parties representing the vessels. These, known as damage surveyors, will carry out nature and extent surveys of the damage. Each of the damage surveyors will usually be allowed to carry out a without prejudice survey on the other vessel, but not allowed to communicate with any of the crew. Each surveyor will then carry out calculations to estimate the extent and the cost of repairs, and they will also need various ship's plans to obtain the necessary information and carry out those calculations. This is an example of a spreadsheet showing damage to a vessel. This is then the side shell. And you can see we've listed the areas on the left-hand side. Here we have what the damage was, what the recommendations are, crop and renew, how many there are, what the length is in millimeters, what the width is in millimeters or height, what the depth is or the thickness in millimeters. And then two calculations are carried out, one the area and one the weight in kilograms. These are then totaled at the bottom to give you the total amount of steel weight repairs required. Notice this is 156.8 tons. It's interesting to note that figure. I'll explain later. Here's the other vessel. Again, this is bow damage. Same principle, tabulated with the areas and volumes calculated. And you'll see that, interestingly, this one is 151.2 tons, almost the same as the struck vessel. And I'll explain why that is later. In the event that there is no agreement between the parties on the apportioning of blame, another marine surveyor or consultant will be appointed on behalf of each vessel. This is the speed and angle of blow analysis surveyor, or the SABA surveyor. And basically what he's doing, he's going to assess the damage and give an expert opinion as to the speed and angle of blow of the two vessels at the time of the collision. He's appointed to carry out an independent analysis of both vessels and give an opinion as to speed and angle of impact. Agreement between the two SABA surveyors that each is allowed to carry out a WP survey of the other vessel. So they will look at one ship, assess the damage, carry out their calculations, brief calculations, and then they'll go over to the other ship and do the same thing. Both surveyors are not allowed to communicate with the crew on either vessel. This is because their calculations are supposed to be based purely on the physical damage. Surveyors will measure the damaged areas in much the same way as the damaged surveyors. However, they will also measure various angles and depths of penetration in relation to frame numbers. They'll need various ship's plans for the necessary information, for example, the shell expansion, general arrangement, capacity plan, and midship sections for relevant areas of the vessel. The plans usually obtained by the lawyers and distributed to the surveyors. Scale plan drawings of each vessel are drawn, then fitted together to show the approximate positions of the two vessels at the time of impact. And of course, computerized drawing packages allow this very easily now. It can be on paper, but generally nowadays computerized. This will give a relative angle between the two vessels. So on site, if you remember the two ships we just looked at, and we looked at the struck vessel, we went out there on a launch, and we were able, by moving the launch up and down the port side of the vessel, to get a rough angle of the collision. But then, of course, later we drew these drawings to confirm what that angle was. And this is how you put them together. So here's a plan view of the bow of the struck vessel, which is known as Vessel A. And this is the striking vessel, Vessel B. This was, in fact, a tanker, and this one was a general cargo vessel. So you can see in this figure one, the estimated final position of the two vessels. So Vessel A is a tanker, and Vessel B a general cargo ship, and the penetration takes place in this direction. So the mechanics. It's possible to determine the collision angle at the moment of maximum penetration. For all practical purposes, this will correspond to the actual collision angle, as penetration only takes a matter of a few seconds. For example, a vessel making 16 knots, striking another vessel on her side, and penetrating 9 meters into the hull before stopping, will have an average speed of about 8 knots or 4 meters per second. The penetration will take less than 3 seconds, such that the struck vessel will only turn a few degrees. So the initial strike will be here. Because this vessel is moving forwards, this vessel will also start to turn in this direction due to the movement of Vessel A. And that's why you get this creasing of the shell plating here, as you saw previously. The bow of the striking vessel will make its first contact at this point here, point C. And from that point, the shell plating would be cut along almost a straight line, making an angle of approximately 45 degrees. And that shows that, so this is the profile of the bow of the striking vessel cutting into the side shell plate of the struck vessel. And the angle of this section here will depend on the stem rake and the stem rake angle and the bow flare of the striking vessel. Further aft, the shell platings and internals would be destroyed. Vessel B's port anchor would cause additional damage to vessel A about 2 meters below the main deck. And this, if the anchor has penetrated the side of the other vessel, then that is a good indicator locating the two ships later. When the corresponding damage is fitted together, as in figure 1 using scale diagrams, the collision angle, that's to say the angle between the bows of each vessel, will be found to be approximately 78 degrees. Damage to a traditional bow, that is with no bulb, tends to be insignificant compared to that of the struck vessel due to upward sliding. However, bulbous bows are of stronger construction and contribute to more damage sustained to the struck vessel, with corresponding damage to the bulb structure. Bulb also reduces the upward movement of the bow during the collision. This may result in the cost of repairs being similar for the two vessels. As we noted earlier, the amount of steel repairs was similar, cost similar obviously. That was because the striking vessel had a bulbous bow. And this shows why. So here's the striking vessel, here's the struck vessel. If this was a traditional bow, this vessel B would have slid, it would have damaged the shear strake here, but it would also have ridden up over the side of the ship. But of course, because of the bulbous bow down here, it acts like a wedge and it damages both the shear strake and the rounded bilge, which contributes to the extra material required. And here's a shot of our striking vessel again with the bulbous bow moved up and back and over. And when the bow strikes the decks, the heavy stringers, tank tops, double bottom tanks, and similar strong points breaks down and collapses. The decks of the struck vessel carve through the bow, so this is where the deck of the struck vessel has carved through the bow of the striking vessel and leave a distinct horizontal cut. This is a vessel in Japan involved in a collision with a bulk carrier. And this vessel is alongside, which makes it a lot easier with a nice crease in the bow from the main deck, the shear strake, which makes it a lot easier to calculate the angle. So the position where the cuts end on each side of the bow, so that's here and here, of the striking vessel will give a good indication of the collision angle, providing the shell plating was straight. That's the shell plating of the struck vessel. And if this is parallel body, then that's not a problem. If not, the curvature of the deck plating of the struck vessel must be taken into consideration. So if you're taking these measurements, or when you're taking these measurements, they must be as exact as possible. You must use suitable points of reference, for example, frames, deck houses, hatches, bulkheads, or weld seams. A short cord stretched between points can be very useful as a base or center line. Measurements can be taken at right angles and at fixed distances along the line, e.g. along a center line with spacing equal to frame spacing. And photographs will assist later, particularly if taken at right angles to the object. So what you have is one side of a vessel obliterated. How are you going to measure the damage? Well, you draw a center line down the center line of the vessel with a chalk cord, and you measure from the cord to the damage, and then you can deduct that from the distances, the beam, half beam, using the vessel's drawings. You'll need the displacements of both vessels because the calculations involve momentum, which is mass and velocity. The angle will be formed between the stern of the striking vessel and the stem of the struck vessel is known as, and it's not showing it there, it's same again, you'll see them on the drawings in a moment. Acute angle of turning of the deck plating on leading edge of struck vessel relative to her center line. So we need to know the striking vessel angle, the acute angle of the turning of the deck plating on the leading edge of the struck vessel relative to her center line. The acute angle from the vertical passing through the lower extremity of the leading edge of the tall shell plate of the struck vessel. So that's alpha. We got beta here, but why didn't do those up there? Anyway, acute angle at the top of the bow the striking vessel makes to the vertical beta, which is the stem rake. So this was our ship, which was alongside with the crease in the bow, if you remember. Very easy to stand there and draw a line on the dock and then work out what the angle alpha was. Simple trigonometry. And this is how we measured the rough angle, the collision angle, by going out on a launch, and actually this is where the bow, the bulbous bow of the vessel has struck the side shell. Yeah. And then this is the same vessel in dry dock in Hong Kong, and you can see the full extent of the damage now. The bulbous bow has actually damaged the side shell into the double bottom tanks, or the hopper plate, the hopper tank, and the rounder bilge. Number 3-4 bulkhead obviously damaged, the shell plating, and also the shear strake, and the hatch covers were damaged as well. This was the one in Japan with the general cargo ship, Vietnamese general cargo ship, when she struck the side of a bulk carrier. What happened there, as a matter of interest, was the two ships were traveling in parallel up under the bridge between the islands, and the master had been on autopilot, and he told the crew member to take the ship out of autopilot. Unfortunately, the wheel was on full over to port, and she just veered around to port and went straight into the side of the other vessel. And that's a closer angle of the damage, and this is basically the collision angle here. Sorry, go back again. The angle here. Okay. Now, estimating the speeds. The opinion is formed, is it dependent on the nature and magnitude of the damage, and by roughly estimating the kinetic energy, a function of mass and velocity. A substantial part of the kinetic energy is absorbed by the water masses set in motion during the collision, but that's equal on both vessels. And the amount of damage will depend on the collision angle and the strength of the damaged structure in the direction of the relative velocity. There are many variables involved, and this is why opinions can differ. So it's desirable to find a more precise method of estimating speed. Not possible to find the speed of each vessel separately, as damage is a result of the relative speeds of the two vessels. Now remember that we are doing this independently. We're getting no information from anywhere. We're not getting any information from VTC or from GPSs or anything like that. We're doing this cold with no other help at all. Obviously, that information can be used later to verify speeds, etc., if necessary. The terminology used is that adopted by Minorsky to differentiate between the two vessels. That is to say, vessel A is the struck vessel, having side shell damage, and vessel B is the striking vessel, having bow damage. That's an interesting fact, that half of the vessels have bow damage, half the vessels have side damage. Minorsky states that the depth of penetration is a function of the relative velocities, displacements, the angle of blow, and the physical characteristics of the structural members, which have significant depth in line with the axis of penetration. These characteristics are expressed in terms of a single resistant factor called RT. When measuring the damage, the following angles must be measured. So remember, this is the side of our vessel with the bow of the imprint of the bow of the striking vessel. So alpha is the angle of damage formed by the bow of the striking vessel. And then beta is the angle due to the rake of the stem. Moving on. So now if we look at both vessels showing relative angles, if A had been stationary, that's this vessel, B would have cut through A along that line AB, straight through there. But unfortunately, because this ship is moving forward, it slides backwards down this line here. Because of A is making headway, the cut is found to be along the line AC, as we just said. The first part of this cut will usually be a straight line and curved further in indicating a change of speed ratio. So as she enters straight here, it may curve round a little bit due to the speed of the vessel heading in this direction and the two slowing. The relative angle eta is the angle of relative velocity, that angle there. These are the two angles that we had a question mark before. So if measured where AC is straight, it will give the angle of relative velocity such that the speed ratio will be vessel A over vessel B is equal to sine of phi minus eta over sine eta. And those explain the angles. Under the Halla analysis, it's slightly different. He uses the profile of the striking vessel more, in that when B hits A initially, he strikes at the point 1. Then as the vessel moves the striking vessel moves into vessel A, it moves the distance B. So this distance 2 here is equal to this distance here. The striking vessel hits the other vessel high up at point 1 first, and then further down at point 2. Later such that when point 2 make contact with the striking vessel, will have moved forward a distance B. Vessel A will also have moved forward so that the point 2 has moved the distance A. Okay. That should be A, sorry, not B. Correction. So if you look at these, this is the Halla calculation. So vessel A's speed over vessel B's speed is tan of alpha over tan of beta. Now, let's have a look at the energy dissipated in the collision, because this is critical. Minorsky obtained the data from 50 collisions from the US Coast Guard for his calculations. These included speeds, angles of encounter, displacements, and drafts, together with the location of damage. So this clearly was evidence after collisions had been carried out and all the facts had been found. So these were historic records. Some were eliminated due to the lack of precise structural data, and collisions with too sharp an angle of encounter were also eliminated. That's because at a right angle collision, the material resisting is at right angles. But if you start to vary the angle more and more, the resistance is not then the same. 26 collisions in the end were analysed for kinetic energy and the extent of damage. He then plotted the calculated resistance factor RT, so this is calculated from the damage to the vessel, as we'll see, on the y-axis, against the calculated absorbed energy in collisions where the speed and angle of blow were already known. These points established a fairly consistent correlation between resistance factor and lost kinetic energy. There was considerable scattering of points at low speeds, and more damage was done than anticipated from the speeds involved. Shows the crosshatch area in the following graph. So here's the graph. So these are the low energy points, low speed, low energy, and these are the other 27 that he had plotted. So resistance factor is up this vertical scale, the kinetic energy along the horizontal scale, and he came out with an empirical formula E equals 415.5 times RT plus 121,900 tons knots squared. So that's the empirical formula. So from the plotting of the collisions, this one was for 10 to 16 knot. Oops, sorry, go back. This one was for 10 to 16 knots. And then what he did was he actually did plot the lower ones and worked out that with this calculation, this was for vessels traveling below 10 knots. Okay. So it states that the kinetic energy absorbed in the collision. So that's one. Let's go back a couple of steps. So this is our first formula. Remember this formula here, okay, as we've done here. They also calculated that the energy absorbed in a collision between two floating bodies approximates to the energy equals the displacement of A times the displacement of B, brackets the velocity of B times sine phi squared over 1.43 times displacement of B and 2 times displacement of A. Okay, moving on. So remember our first equation that he got from the empirical formula? So you can equate these two now. Now, knowing the displacement, so we know displacement A, we know displacement B, and we know we're going to calculate RT in a moment. So what we're going to get out of here is, if we know the angle here, we'll get our velocity out. So knowing displacement angle, and by calculating RT, we can find VB. RT is calculated for the damaged structures of both vessels, where RT is the frictional resistance of A plus the frictional resistance of B, where RFA is resistant factor of struck vessel structure and RFB is resistant factor of striking vessel structure. So on vessel A, the struck vessel, the structures considered for RT are the decks. So this is the horizontal material, which is going to be resisting the bow as it comes in, cuts in. And horizontal sections of frames, vertical stretch sections of frames, and stringers. On vessel B, they comprise the stem plate. So you've got the stem plate, which is reinforced. The forecastle intermediate decks, so you've got the decks at different levels in the forecastle store, forepeak, and then you've got the centerline girder and the stem girder. The resistor, and this is the key to the calculations, is knowing which material you have to go and measure to find out what the extent of the resistance. The resistance factor for each vessel is derived as follows. So it's tabulated. It's quite simple. You take the deck. This is the penetration times the length times the thickness of the material, and that will give an RFA. This is for vessel A, where P is the maximum depth of penetration. Note these are in imperial units. L is maximum length of damage at shell, and T is the thickness of the member. For vessel B, then this is obviously the striking vessel. It's going to be the centerliner girder, intermediate decks, and stem girder. Again, penetration, length, and thickness. And then if there's any shell damage, of course, that's also resisting. So, if you note, we have some notes there. Where are the notes gone? No, we didn't do it. Never mind. Okay. So the thickness of the transverse frames is distributed over the maximum width of penetration at the ship's side, and may be added to the thickness of the deck plating. The geometry of the girders is assessed as an equivalent flat plate, for example, the volume of the offset bulb plate being added as a flat plate. So if you have OBP frames, OBP beams, that little bulb on the end or offset bulb is additional material. You can add it on as flat plate. And then stem damage in where the forecastle store, that's also included. It should be noted the above calculation we're using imperial units as the initial work was carried out before SI units were adopted internationally. Consequently, when using Minorsky's method, a conversion factor must be applied to make allowance for the use of SI units. So the above tables may thus be represented as, so now what we do is that there's all our information on the struck vessel and the striking vessel, P, L, T, and you notice there's an LF here and an SC here. We'll come to those in a moment. But this is the conversion factor to take it from imperial units to SI units. So you'll notice instead of using feet and inches, we're now using meters and millimeters. I trust that you're all going to get a copy of this presentation in a PDF format later. So you notice those two factors I just pointed out, LF and SC. LF is the length factor, Minorsky recommending 1.33 for ships traveling at 10 to 16 knots. This takes into account the forward motion of vessel B and its increasing penetration into vessel A's side shell. And the shell component, Minorsky recommended 0.7 for ships traveling at 10 to 16 knots. The shell component takes into account the reduced transverse strength of the side shell of the striking vessel. So it's not like a vertical frame or a horizontal girder. It's just like this, the side shell on a car. You can punch it in with your hand or with your foot. It's a lot less strength than the vertical members. It's all to do with second moment of area. So here's an example of the calculations we've done, and you'll see calculated for the struck vessel and the two lots of striking vessel, and then added together at the bottom here to give a figure. What we do is I've designed a spreadsheet to automate this process. So we put this information into the spreadsheet. So here you'll see we have the displacements of the two vessels. So what you will need to do here, of course, is if this is mid-voyage, you will need to take the condition at departure port and obviously subtract consumptions for fuel, fresh water, etc. Same with both vessels. Then we've put in the angles, so that should be eta, 25 degrees, converted into radians, because we use radians when we're calculating, obviously. Phi, the angle of blow from the observation, which we thought was 55. Acute angle from the vertical passing, so that was alpha, 47 degrees. And the acute angle of the vessel strike, that's the vertical, in other words, the rake of the bow. Now remember here that ships tend to be trimmed by the stern. So obviously if you've got a 1.5 meter trim by the stern, the angle of the rake obviously reduces. So you have to also calculate how much that angle is reduced to make it accurate. Sorry. What we've done is added in here the calculations in here. These transfer across into here, and further down the calculation is carried out. Okay, so remember this formula originally. So knowing RT now and displacements the two ships and the collision angle, we can solve for VB, and then using this equation or this equation, so this was Halla, this is Minorsky, we can calculate also the vessel A speed. And what we can do is we can equate those like that. Then what happens is in the spreadsheet, we get an output data. So we've got the input data page I showed you. This is the output data. So it gives all the input information here. And this gives the actual speeds and angle of blow here. Quite straightforward. Saves a lot of time and energy. If you want a copy of that, you can get in touch with me. Now you have to put a report together, which is basically an expert opinion. So the report should include principal particulars of both vessels, the parties attending the surveys, obviously, general arrangements, each vessel showing the damaged areas, backgrounds the incident, details the damage sustained to each vessel, basically descriptive with maybe a sketch, and you could use that table of found and recommended as well. The angle of blow assessment is a breakdown of the collision with evidentiary damage. And then you have to give the information you've used, so the drafts of both the vessels and displacements. Should include also the availability of any supporting evidence that may be available from external sources, but you wouldn't use these until after you've carried out your calculations, right? Diagrams showing relative sizes of the two vessels, the estimation of the speeds and angles at the moment of impact, table showing impact data and results, and a diagram showing the speed and angle of blow. Then you have to give your expert's declaration, which basically says, I did this, nobody interfered, this is my opinion only, and I'm basically a servant of the court and not of my client. Okay, and I understand I'm going to be cross-examined if we do go to court. Those of you who do expert witness work or expert opinion work will already know this. Then it's very useful, obviously, because a picture says 1,000 words, to actually put some diagrams in showing what's happened. So in the case of the Vietnamese vessel, this is the bow damage here. Just a very, very simple plan view showing the hatches, double bottom tanks, etc., holds. And then the struck vessel, the bulk carrier that got hit, the Japanese bulk carrier, and showing where the damage occurred. And then if you can draw a picture of the actual damage, the side of the bulk carrier was obviously submerged. And we got this from the divers, they drew this. And you can remember that we saw the deck, this was the area on the deck that we saw in the picture. And then you have to show the relative sizes and drafts of the two vessels. And then that will explain why you've got damage in certain areas. Then this is your diagram showing the speed and angle of blow at the moment of impact. And this is the product of your calculations and what the client is looking for. So vessel A was traveling at roughly 11.59 knots. Vessel B was about 9.83 knots. And this is the angle, which was 57.69 degrees. That's what he's looking for. That's what you get paid the film star wages for. And you show these angles also. These are the angles that you've used in the calculations. Now, it's also useful to show, because there will be other damage down the side of the vessel or in the bow of the vessel, it's useful to show the damage which occurred after the event. So, come on, there we go. So this is colliding, come on. So you see vessel B is now drifting down the starboard side of the struck vessel. Until you get separation. So, summarizing. As the structure of each ship is subject to complex progressive failures by buckling of panels, shearing, tearing, crushing, bending, and twisting of plates, and I'm not going to add any sound effects here, and shapes beyond the elastic range for steel, resistant forces do not lend themselves to a finite element analysis. It's therefore necessary to keep any calculations as simple as possible. And that's where Minorsky's analysis has been tested over time and found to be accurate enough for our purposes. Come on. To ensure appropriate results, the input information must be accurate. This will give confidence in the results. And using spreadsheets will allow the automation of the calculations, as I've showed you. Diagrams and graphics will assist in reporting and understanding by principals. Advisable to learn how to measure and carry out calculations under an experienced proponent of the subject. which is unfortunate because if speed and angle of blow, if collisions occur, the lawyers usually want you out there as soon as possible. You don't have time to phone your friend and invite him to come from Manila or wherever to witness what's going on. So further, with the introduction of navigational simulators, it's now possible to completely automate the scenario. Successful tests have been carried out using the Transat Maritime Simulator software on a laptop. Key parameters for the two vessels can be input to the software. It's followed by the scenario stated by the master of ship A, then that for ship B. When run to its conclusion, it's likely the two vessels will miss each other completely. If the Sabre surveyor's calculations and scenario are then input, the collision events can be confirmed. This information can then be used at a without prejudice meeting between lawyers and experts to resolve the issues. Not yet tested in court, however. Other information, I've mentioned that we've designed a spreadsheet which you put into the information in is the angles used in the calculations, displacements of the two vessels, as I showed you, estimated angle of blow, damage measurements. The results are then shown in an output table giving the absolute speeds and angle of blow. And also I've written a training module on this, on the subject, with worked examples and test cases, if anybody would like to take it further. So just contact me at my email address. Moving on. And due to the methodology employed in these calculations, I call this method the 3S system, which most of you will know means simple sums for sailors. Okay, so I have one more to bring you to this one I want to share with this one. Okay, quickly before we go on, before we finish, if you're involved in the investigation of collisions, very often, and obviously after the fact, it's very difficult to give visual representations of what's going on. So the simplest way of doing this is using the old flip card methodology, where you used to flip through cards and see a movie happening. And you could very easily do this with, sorry, just taking a little bit. You can do this very easily with PowerPoint by staggering the slides half a second. So here we have a case of a large container vessel coming out of Busan, almost up to full speed. And this small Russian-Ukrainian trawler had been in for 3 months doing repairs and was out undergoing trials. She was doing about 10 knots. And the Iran Command was doing about 17 to 18 knots. And the structure of this vessel had these side structures with the working deck between, which meant for the master to see what was going on behind him, he had to walk out onto the starboard bridge wing and look over his shoulder. And he did this, and he saw the Iran Command coming down towards him and about to sink him. So he initially turned to port to get away from the Iran Command, but then what he did was he put his stern directly in line with the Iran Command, and then he realized he was going to be overridden very easily. So this is the events. These are the events. So these the relative speeds of the two vessels, Iran Command, sea wind coming down. So as she comes passing her, you get the interaction between the two vessels, so she gets sucked into the side of the container vessel. The second mate on the bridge then realizes something going on and shouts, "Starboard!" So the ship goes to starboard, smacks the side of the trawler, and takes off. And he didn't stop either. He kept going. And this was the resulting damage to the trawler. So this is the after roller down the back here where the nets would be brought up. These structures on either side of the vessel are actually deck houses with ice-making machines inside them. So this is dropping ice immediately onto the fish. And you'll notice there's a door missing here, okay? Unfortunately, in this case, there were 4 people killed and about 15 injured, because she was also a factory ship, processing ship. The Iran command, when we caught her in Hong Kong, you can see the damage here from the strike, the collision. And we went on board to interview the officers. And no, we were nowhere near it, sir. Nowhere near it, sir. No. So I said, well, if that's the case, do you think we can have our door back, please? That's actually the door off the ice making machine on the back of Sea Wind 1. Okay, so case closed, and the whole case was resolved. Okay, thank you very much. That's me done.
Mike, it's Mike Schwartz back online here. Had a bit of kip. Thank you ever so much for delivering that presentation. Fascinating stuff. And did you get your door back, I suppose, is the question I have for you.
I think so.
Does anyone have any questions for Mike? Anybody want to raise a point or two? Yeah.
Deathly hush.
You've silenced them all, Mike, with your presentation. So, Mike, thank you very, very much for your contribution to the Marine Surveying Fest. Right, so it's